In this part, we will look into basic NFS protocol and see how these operations are used by the client when it is exposing a regular file system interface to the user applications. So operations at NFS layer, there are like 6 basic operations. Lookup, lookup actually gets back the file handle, given a file, given a directory handle. Lookup gives back the file handle corresponding to the file along with its attributes. So lookup takes directory handle as the first argument and the name of the file inside the directory as a second argument, and it returns the file handle corresponding to the file which is under the directory. The request fails, of course, we return uh, error, right? So similarly, we have create, which creates a file under given directory, and remove removes a file under given directory. Read reads a file which is specified by the file handle at the corresponding offset, and count indicates number of bytes to be read, and will return the data which is of size count if there is so many, if the count number of bytes are available. It returns the data and returns attributes, the new attributes for the file. Similarly, write also does the same thing. It also returns attributes. So note that every operation, okay, along with returning whether the operation succeeded or failed, you always get attributes back, indicating the current state of the file on the server. Okay, this allows client to do or like expose the current state of the files of that corresponding file to the user. So what's missing from this operation is the close. Okay, there is no close call here, or like there is no function close that is supported by NFS, because there is no need to tell the server, because server is stateless. So server doesn't remember any file that is opened by the client. So there is no need for the client to tell the server that it is closing a file, because every access to a file always uses the file handle. So there is no open. Similarly, there is no open, because open actually translates file name to file descriptor in case of regular Unix file system. But in NFS, there is no open. So all the accesses happens by using file handle. And since there is no open, there is no file descriptor that is stored for each file. So consequently, there is no need to have close. Now, how can we use these operations on the client side to implement a file system? Okay, to expose a regular file system to the user. So here, let's look at the first function, lookup, right? So lookup returns the file handle instead of file descriptor. And file handle actually specifies the unique location of the file, which is interpreted by the server. So for instance, if I want to, let's say, access a certain file inside directory, so first I get the directory handle, and then using the directory file handle, I if I want to access another file inside the directory, so I use the directory file handle as the first argument, and the name of the file as the second argument, and then call lookup. So lookup returns file handle and the new attribute and the attributes of that file. So of course, lookup also does the access control. It needs to make sure that the client or client who is making the request on rather the user under like who is making the request has access to the file. If yes, then you will get back the corresponding file handle, else uh, failure will be returned. So now let's given a file, given a directory path or like given a file path, so lookup will be called many times by the client, right? So user just gives the path of the file and calls open, but under the hood, client needs to make many lookup calls, which are RPC calls to the NFS server. So first we need to look up folder user in the root file handle. So the root file handle will be provided by the NFS server by using mount protocol. So the root file handle, let's assume that root file handle is given to the client beforehand. So now using root file handle, client will ask for user folder inside the root file handle, which returns file handle 0, and then it uses file handle 0, ask for Joe, which is the second directory, so on and so forth until we reach list.txt, our final file. Okay? And this file handle will be stored by the client side, not by the user, but on the client file system layer. Okay? Similarly, now other calls, for instance, let's say now open. Let's say when the open system call on the client side, in case of if the client is Unix. So here, open is now a series of lookup calls, right? Because open needs to return file descriptor, and to do that, client side needs to maintain a mapping from file descriptor to a corresponding file handle. So here, first we do lookup of that file, we get the appropriate file handle, we record the mapping from the file descriptor to the file handle, and set the initial offset to 0 for that file descriptor and return the file descriptor to the user. Now let's say when user does read, then we get the correct current offset for file descriptor, and then we convert the file descriptor to file handle because we have stored it open, right? So we get the file handle for the corresponding file descriptor, then we perform RPC call using the file handle at the stored offset, and then once the RPC returns, we copy the data back to the user buffer and then increment the offset by bytes. Similarly, write will also be implemented in the same way. Okay, where we get the offset for the file descriptor, convert file descriptor to file handle, perform write RPC. First copy the data from user space to the kernel space, and then perform write RPC, and then increment the offset by bytes. Okay. And the Unix system call, like close, we don't need to do any RPC, just need to remove the handle. We just remove the mapping of the file descriptor. So we remove the mapping from file descriptor to file handle in the file system, and that's it. We don't need to tell server because server is stateless. It doesn't remember which client is accessing which file. So now, so what does file handle contains, right? So as we saw in the in all the previous interactions with the NFS server, we use file handle. What does file handle contains? So can we use inode for file handles? No, right? Because inodes, we assume that inodes are constant for each file system. Okay? But there could be multiple file systems that are that 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 the NFS server might be serving. So we cannot have uh, just the inode as the file handle. So what file handle contains? It contains three parts. First is file system ID. So this is the ID identifying the disk partition where that file is located, disk partition of the file system basically. And inode number is the actual inode number of that file in this particular disk partition, which is local to that disk partition. Okay. And then inode generation number is a number that changes every time the inode is reused. So this avoids, like, inode generation number is important in avoiding uh, is important in like maintaining a temporal uh, consistency. What it means is, let's say there are two clients which are accessing a file and they both have the same file handle. And let's say one of the clients deletes the file handle, deletes the file, and then and other client is still using the file handle. Okay, it is not making any RPC calls, but it is still has the file handle. So let's say one client deletes the file and it creates another file. Okay, and like NFS, let's say since the inode is free, let's say if it uses the inode for another file. Okay, in that case, when the other client, when it tries to make an inode call to the file handle, if inode generation number is not used, then there could be a conflict, especially when the inode is reused between consecutive calls. So inode generation number breaks this, because when inode is reused, since the inode number changes, inode generation number changes, in that case, if two file handles, if they belong to this, if they belong to indeed different files, then the inode generation number would be different. That's how NFS avoids conflicts. So one of the design objectives of NFS is to perform fast crash recovery. So this is actually the main reason for the stateless design. So stateless design stateless design is one of the key ideas of NFS. Okay, so here the server doesn't like is not required to remember anything about the clients. Okay, like which clients are connected, which clients are open, which files are used by which clients, whatever. Okay? It doesn't need to remember anything. And clients, it's the responsibility of the client to make sure that all the information that is needed to service a request is provided in the request itself. So client needs to make sure that all the request contains all the data that is needed to perform the request. Okay? For instance, like for every read and write, client actually needs to specify the offset in the file. Okay? And we will see how this is important for fast crash recovery in the next slide. And another key idea is the server operations are idempotent. That means like if you do the same operation multiple times, the result will be same. However, I mean like it depends on the operation, but most of the operations the result is the same, right? So for like a simple example of idempotent operation is A equal to B plus 1. So irrespective of number of times you run this instruction, the result is the same, right? Whereas non-idempotent operation is A equal to A plus 1. Here, depending on the number of times you run, the value of A changes. Okay. And this idempotency is also important for crash recovery, because if the crash happens, client can always redo the operation without worrying about consequences, because irrespective of the number of times we do the operation, the result is the same, right? So this is important for crash recovery. So the consequences of statelessness, reads and writes, as we saw, they need to always specify the offset because server doesn't remember anything. So if user has to, since we want to expose a conventional API to the user, like a conventional Unix API, so it's the responsibility of the client file, like client virtual file system layer, to maintain a local offset that is consistent with the application, right? So crash recovery in stateless file systems such as NFS is very easy, because when the server crashes, client just resends until it gets an answer from the server, right? Because on the client side, like it cannot determine whether the server is crashed or the server is just busy servicing other requests. So there is no way for the client to know whether the server is crashed or it's just taking a long time. So on the client side, crash recovery is very easy. It just performs operation until it gets success from server. Okay. On the server side, we just need to restart the server. That's it, because server doesn't maintain any state. Okay. So if after we restart, server should just come up and it should just keep on servicing the requests. Okay. And all the clients that are uh, that are active will still use the server as if no crash happened, because there is no way for the client to know about the crash. Similarly, server just boots up and it doesn't need to do any client specific recovery, right? So in the next part, we will look into another feature of NFS, and basically performance. How does it provide decent performance along with being stateless?